state and prove a more general form of the inclusion-exclusion formula for a while now, so let's just collect what we have already. Some things that we know. We have that, oopsie daisy, we have that basic inclusion-exclusion is the size of A union B equals the size of A plus the size of B minus the size of A intersect B. And we have this corollary which says if A intersect B is nothing, then we have the size of A union B equals the size of A plus the size of B. That's what I called corollary 1 down here in this previous example. All right, lovely. So now I want to state, I want to remind you of one more thing. We have some extra notation, which is for any natural number n, I'm going to define square brackets around n to be, so I'm just defining this as the set 1, 2, ... up to n. So you might hear this called an interval of natural numbers or an interval of integers. But it's fairly standard notation. So now here is, this is inclusion-exclusion for 2 sets. This is a special case. So now here's the general inclusion-exclusion. So this is the general form. And the way that I want to write this is I'm going to say the size of the union, this is an index union as j goes from 1 to n, of the AJs, so I've got some indexed set of sets, some indexed family of sets, A1 through AN, is equal to the sum over all subsets of that interval of natural numbers. And here's what I'm going to do. For each subset, I'll take -1 to the size of the subset minus 1 and multiply that by the indexed intersection, all the indices in that subset of AJ. All right, so what am I saying here? I'm saying I've got an indexed union, and the size of this indexed union is the sum of some sizes of intersections, indexed intersections, where I've got this sort of parity, this plus or minus depending on whether the size of the set is even or odd. All right, so before I prove this, I want to try to just make sense of the statement. So let's just set n equal to 1 and try to make sense of this statement. On the left-hand side, we're going to have the sum as the union as j goes from 1 up to 1 of AJ. Well, this is just the size of A1. And on the right-hand side, we're going to have what? Well, we're going to sum over all possible subsets. So let's consider the subsets of 1. Okay, well what is 1? Well, 1, let's do some scratch work here. 1 is just going to be the set containing the element 1. 2 would be the set containing the elements 1 and 2, etc. So I'm summing over all subsets of 1, that is basically either the set containing the element 1 or the empty set. And then with each of these subsets, I'll do something. So let's just keep track here. Let's do our first subset is the empty set. So when S is the empty set, what do? We take -1 to the size of the empty set, -1 to the size of the empty set, which is, I guess the size of the empty set is 0, -1, and then we'll intersect nothing. So, I mean, that's just going to be nothing. And then we're going to have to add this to the case when S is just the set containing the element 1. And what's that? Well, -1 to the size set containing the element 1 minus 1. And we're going to look at the size of, oh, I forgot size of here. We're going to look at J in, you know, the set 1. Well, that's what we've got. Well, this is going to be, of course, 0. And -1 raised to the -1 power is -1, so it's -1 times 0. Plus, what do I have here? Well, I've got -1 to the 1 minus 1, so that's -1 to the 0 is 1. Well, let me just put -1 to the 0, that's going to be 1. And intersection of AJ as J ranges through this set, well, it's not much of a set, it's just A1. So the size of A1. So the left-hand side is A1, the right-hand side is A1. Okay. If that seemed like a mess, it's because it is kind of a mess. This is a very general statement. And by the way, you'll see other statements. This is just the way that I like to write it. Let's sort of talk through how we do this for n equals 2. Okay, talking through how we do this for n equals 2 in a little bit less detail. Well, so this, if I do this indexed union, as j goes from 1 to 2, I'm just going to have A1 union A2. And let's do this right-hand side. Well, I've got the empty set, so -1 times the size of the empty set, so 0. Now plus, well, I've got, again, for the set brackets 2, that's the set containing the elements 1 or 2, set containing the elements 1 and 2. So first I've got the sets of size 1, so it's either the set containing the element 1, intersecting all the sets in the set containing the element 1 is just A1, plus intersecting the sets that are just A2 is just A2. And now the subsets of bracket 2 of size 2 is going to be, I'm going to have minus, we're summing here, -1 to the size of a 2-element set now. Let's just put this one in because this one's new. Times A1 intersect A2, and this is going to work out to be a -1. And then for n equals 2, we have exactly, just rewriting, A1 union A2 is equal to, well, 0. Got A1, size of A1 plus size of A2 minus the size of their intersection. And we notice that this agrees with the initial statement that I gave you for inclusion exclusion, so that the size of A union B is the size of A plus the size of B minus the intersection. What do we have here? The size of A1 union A2 is the size of A1 plus the size of A2 minus the size of their intersection. Okay, so we could do this for 3 and 4, but hopefully this is enough to understand this theorem statement. So let's now try to prove this theorem, and the proof is not terribly bad. We'll proceed by induction. The base case is check that it holds for n equals 1. And we checked that right up here. So it does hold for n equals 1. That was this thing that we did. So we've got the base case knocked out just by verifying the formula when we first looked at it. So the tricky part, and not even that tricky, is going to be the inductive step. So for the inductive step, we assume it's true for n and show this implies that it's true for n plus 1. So in order to do this, we'll start with our inductive hypothesis, and our inductive hypothesis is precisely the theorem statement. Namely, and I'll just rewrite it here, the index union as j goes from 1 to n of aj is equal to the sum as S ranges over all subsets of brackets n of minus 1 to the size of S minus 1 times the size of the indexed intersection, where j ranges through S, of the AJs. So I'm going to assume this is true for n, and I'm going to try to show that it's true for n plus 1. So in order to show that this is true for n plus 1, what do I need? I need this n to become an n plus 1, and this n to become an n plus 1. Oh, just a side note here, saying S ranges over all possible subsets of this n bracket, I could say S is an element of the power set of n bracket, but I just didn't see fit to introduce even more notation. Although we've seen the power set notation before, it just felt like this was a bit more straightforward. So in order to get this thing true for n plus 1, what I'm going to do is I'm going to consider the left-hand side of the statement for n plus 1. So I'm going to consider the size of the union as j goes from 1 now to n plus 1. So I've added in some n plus 1th set. There's A1, union A2, union A3, et cetera, up to AN. And now I'm just saying, okay, suppose that I want to also compute this union if I'm throwing in, another set, AN plus 1. Well, this is equal to the size of A sub n plus 1 union, well, the union that I already had. The union as j goes from 1 to n of the AJs. This was the thing that I already had. And this is equal to, by my corollary, AN plus 1 intersect this union plus AN plus 1 complement intersect the big union. Okay? So this holds by the corollary that I stated earlier. This, if two sets are disjoint, then the size of their union is the size of their union is the sum of their sizes, and that's really what we've got here. The size of the union of this set. This thing, how am I applying this? This is AN plus 1 intersect the union AN plus 1 complement intersect the union. That's what this set is here. So I'm breaking this set up into disjoint pieces. Okay, so I had the union of n plus 1 sets. I wrote it as the union of A sub n plus 1 with this union of the first n sets, and that is broken up into, well, the part where AN plus 1 intersects with that old union, the part where AN plus 1 doesn't intersect with that old union. And by applying the corollary, I get that this union, which is this union, is equal to this sum. The size of this union is equal to the sum of these sizes. All right, so now what I need to do is I will define a new family of sets. So I'll define BJ to be AJ intersect A sub n plus 1. And I'll define CJ to be AJ intersect A sub n plus 1 complement. Or I could write that CJ is AJ set minus A sub n plus 1. Either one of these is fine. And now this thing right here, I'll call this star, this sum of these two intersections, that has really become the size of the indexed union of BJ's plus the size of the indexed union of CJ's. And why is that? Because, you know, AN intersected with this big union is the union of A1 intersect AN plus 1, unioned with A2 intersect AN plus 1, unioned with A3 intersect AN plus 1, etc. So this, by the inductive hypothesis then, this is the inductive hypothesis, is equal to, well, this, I'm going to apply the induction hypothesis, which says that the size of the union of n sets is equal to this indexed sum. So the size of the union of n sets is equal to this indexed sum. Sum as, let me, instead of using the same letter S, let me use a different letter here. The sum over U being a subset of n, n bracket, and I've got -1 to the size of U minus 1, and then an indexed intersection where J ranges through U of BJ's. So I've got this, plus, now I'll run the same game for C, except for C, instead of using U, I'll use V. So summing over all subsets V in N, where I've got -1 to the size of V minus 1. And now I've got this indexed intersection where J ranges through the set V of CJ. Okay, so let's see what we've got here. We're almost finished. Notice that each subset here is going to include each subset U here is going to basically be the same as a subset S from our original set N, but also include N plus 1. Okay, so these will be like AJ's with AN plus 1. Similarly, every subset here, every V when it's a subset here, is going to give me an intersection. I guess it's not the subsets, it's the intersection will be like a subset with some elements from the first N, and then including an element, including the element N plus 1. And this will be like the AJ's without A sub N plus 1. Meaning that summing these two sets together is just the sum, and I'll now call it S subset of N plus 1, because if it was a subset that included N plus 1, it would come from this term, from this sum. If it was a subset that did not include N plus 1, it would come from this sum. And then we've got what? -1 to the size of S minus 1. The size doesn't change. It's either a subset here or it's a subset there. And it's the intersection as J ranges through S of AJ. And this is precisely what I wanted for the right-hand side of my induction. So I hope that made some sense. Have a great day.